So what we're going to look at today is we're going to look at separation of variables, which is a technique for solving differential equations, for finding the solutions to differential equations. And if you remember, this is the basic thing that we want to do when we're working with differential equations, is we want to find their solutions. Now, it turns out that differential equations come in a lot of shapes and sizes, and not every one of them is going to be able to be solved using separation of variables. This happens to actually be the most basic way, all right? The one that kind of ends up being the most intuitive and the one that goes along with calculus the best. So we're going to show how to do it, and hopefully that'll give you a taste of differential equations before you actually get into the full class. Okay? So let's consider a problem. Let's consider the differential equation. We have dy dt is going to equal t over t squared y plus y. And our goal here is to notice that if I can integrate, okay, so integration of the derivative gives me the solution. So the whole goal here is to be able to integrate, right? And we're going to end up integrating both sides. That at the end of the day, whenever we're doing differential equations, that's kind of what we're going to try and do, is we're going to try and integrate both sides, right? And that's what separation of variables does. It allows us to integrate both sides. What we're going to think about this, we're going to think about this from this perspective. Imagine that what I have is I have df dx, okay? And it ends up equaling some function of x, okay, over another function of f, right? Or maybe if it's easier to think about, we have dy dx, and then that's going to end up equaling some function of x, okay, divided by some function of y. What I'm going to do with that is I'm then going to say, okay, well, if I can just move over the y's, then I get g of y dy, okay, will equal, and I'll move over my x's by multiplying, basically by cross multiplying. I get f of x dx. And this isn't exactly what's happening, but it's kind of the idea that we use for separation of variables. What I now have is I have something that I can integrate both sides. And so what I do is I go in and I integrate. I get g of y dy, right, equals the integral of f of x dx. And what I'll get, generally is how we'll write it is we're going to write a g of y, some function of y, is then going to equal big F of x plus a constant c. And that's the solution to our differential equation. And that's how separation of variables works. So let's see how it kind of like plays out when we do this particular problem, because I think seeing it done will make it a lot more clear. Okay? So what I want to do is, on this side, the side where I have my functions, I need to separate it. I need to separate it into functions of t and functions of y. All right? So I'm going to have dy dt, okay, equals t, and by factoring out a y, I'll get y times t squared plus 1. So now my y's and my t's are actually separated. Now what I can do with it is I can actually multiply over my functions of y and multiply over my dt, right? Or basically separate my variables is what we call it. And it's not really multiplication, but again, it's kind of the basic idea. So we end up with y dy is going to equal t over t squared plus 1 dt. So now my functions are now separated. So what I can do now is I can take the integral of both, all right? And that's what I'm going to do. I'm at the point where I have my t's and my y's are separated. Once I'm to that point, then what I'm going to do is integrate. So now this is going to end up giving me 1/2 y squared. And what I'm going to do is I'm at the end, so I'll write this as, call it c1, okay? And then this is going to end up equaling, well, this is a u substitution, so we'll let u equal t squared plus 1. And we'll let du equal 2t dt. So consequently, what this means is that 1/2 du is just going to equal t dt. So what we get now is the integral of 1 over u du times, right, times the 1/2. So there's the 1/2 out there. So what that then gives me is 1/2 of y squared plus c1 is going to equal 1/2 the natural log of u in absolute value plus c2. By replacing t squared plus 1 with u, what we get is 1/2 the natural log, and t squared plus 1 is always positive, so we can just keep it like that. We don't need the absolute value any longer, plus c2. Now, what's going to happen here, so what that gives me is that's going to give me a 1/2 y squared plus c1 equals 1/2 natural log of t squared plus 1 plus c2. So what I'm going to want to do now is I'm going to want to like bring over everything. I want to isolate y, if possible. Sometimes you can, sometimes you can't. But we're going to want to isolate y, if possible. Okay? And so what that means is I get 1/2 of y squared, and that's going to equal 1/2 natural log of t squared plus 1 plus c2 minus c1. Now the fact of the matter is, this is just a single constant. Right? It's just a single constant. So what I'm going to do is I'm going to combine it together as a single c. And we're going to do that all the time. We're going to change constants, right, whether or not they be divided by other constants, multiplied by other constants, or if we subtract or add other constants, we're just going to combine them together into a single c. Okay? So what this gives me is it gives me 1/2 y squared is equal to 1/2 the natural log of t squared plus 1 plus c. So if you see me doing that or see other people doing that, that's what's going on. We just combined our constants. And in the future, I'm not even going to include this one over here, okay, because it's going to be moved over to the right-hand side anyways. Now what I want to do is I'm going to take this, and this is going to end up being, I'm going to multiply by 2. This will give me y squared equals, and then this will be 2, right, times 1/2, so this will be the natural log of t squared plus 1, and then plus, and this will become 2c, but 2c is still just a constant, so I'm just going to make it c again. I don't actually need to change that constant just because I multiplied it by a number. It'll all come out in the wash anyways when we actually go out and solve for our particular solutions or find our initial conditions, or use our initial conditions, excuse me. Now what I want to do is I want to take this, and I'm going to take the square root, so y is going to equal, okay, plus or minus the square root of the natural log of t squared plus 1 plus c. And there we go. And that's our that's the solution to our differential equation, or our solutions. This is the general solution to the DE. Okay? So let's take a look at what we did. So I started out and I said, okay, well what I want to do is I want to separate out my y's and my t's, just by doing a little bit of algebra. And how I did that in this case is I actually factored out a y and left me with t over t squared plus 1. Once I've done that separation, then I just go in and integrate. I integrate and simplify, and that's the entirety of the process. What we want to notice, a couple of things that we do that are kind of conventions, is we combine our constants, okay? And if I multiply or divide my constant or add another constant to the constant, I just replace it with a c. Just replace it with a constant. The difference is that sometimes if we have like higher order differential equations, what we're going to do is we're going to have two different constants and we actually have to represent them as different constants. And in that case, we'll be very clear to call them C1 and C2. All right, let's take a look at another example. Now let's solve this initial value problem. We've got y prime is equal to 12xy minus 2x, and we'll let y of 0 equal 15. So what I'm going to do first is I'm going to rewrite this as dy dx for my y prime is equal to 12xy minus 2x. Now what I need to do next is I need to go out and separate. So now we separate. So this now gives me dy dx, and I'll factor out a 2x. It gives me 2x times 6y minus 1. So now my x's and my y's are separated by multiplication, which is good. They don't separate by division, by addition or subtraction. We want to separate them by multiplication. So what I'm going to do now is I'm going to really separate them. So this is going to give me now 6y minus 1 dy is going to equal 2x, or excuse me, dy over 6y minus 1 is going to equal 2x dx. Now that we're fully separated, we integrate both sides. dy over 6y minus 1 equals the integral of 2x dx. This side, we'll use a u substitution, so we'll let u equal 6y minus 1. And so du will equal 1/6 dy. And so consequently, 6 dy. And so consequently, dy is going to equal 1/6 du. So what this means is that I now get the integral, or 1/6 of the integral of 1 over u du is equal to, and then we'll just take the integral of 2x dx, which is going to end up being just x squared plus c. And in this case, in this example, I'm not actually going to include my constant here. I'm just going to absorb it into the constant on the right-hand side. So this is now going to give me 1/6 times the natural log of u equals x squared plus c. So now 1/6 the natural log of 6y minus 1 is equal to x squared plus c. And so now what I'm going to do is I'm now going to solve for y. So this is now going to give me the natural log of 6y minus c is equal to 6x squared, and we'll absorb the 6 into the c. So 6x squared plus c. Now what I'm going to do is I'm going to take e to the ln of 6y minus 1 to get rid of that natural log, and that'll equal e to the 6x squared plus c. Now this next step is actually really pretty crucial, because this is how you're going to see us showing what that constant is, or where the constant shows up inside of problems like this. So now on the left-hand side, I get 6y minus 1, because e to the natural log of something is just itself. So 6y minus 1 is now going to equal e to the 6x squared, and by our power laws, okay, we get e to the c, right? So if you think, if we multiply two numbers whose bases are the same but whose exponents are different, or even if they are the same, we just add the exponents. And so that's how we get this piece here. Okay, these two end up being equivalent. Now here's the thing, e to the c is a constant. So we are going to rewrite it as just, we're going to let e to the c equal, we'll call it c1. So this means that 6y minus 1 is going to equal ce to the 6x squared. So that when we actually go about solving our initial value problem, we don't have to take the natural log of anything. We just say, oh, you know what? E to the c is just a constant. I'm going to figure out what that constant is anyway, so I'm going to replace it with a c. Now, I'm going to take this, and one of the things I want to kind of look at here that might make my life a little bit easier is if I go in and notice that y of 0 is equal to 15. So if I plug in a 0 right now, okay, I might get, this might be a little bit easier for me to work with. So let's go in now and solve for c. So let's say, for example, I know that y of 0 equals 15. That's my initial condition. All right? So the reason why I decided to do it at this place rather than going out and solving for y and then plugging everything in is just because if you notice, plugging in a 0 here in for x is going to leave c all by itself. So I'm going to get 6 times 15 minus 1 is going to equal, and it'll be c e to the 6 times 0 squared, right? Which is just going to equal c times 1, which is c. On the left-hand side, I'm going to end up with 89, so 89 is going to end up equaling c. Awesome. So now what I get is that 6y minus 1, okay, so my next step here is that 6y minus 1 is going to equal 89 e to the 6x squared. And now I just need to solve for y. So 6y is going to equal 89 e to the 6x squared plus 1. And so y is going to equal 89 over 6 e to the 6x squared plus 1/6. And that is my particular solution. Okay? So in this video, I've actually demonstrated a couple of really kind of very valuable techniques to be able to do with separation of variables in addition to doing the actual separation of variables. So let's go over the technique one more time. Whenever I want to go in and separate variables, what I'm going to do is I am going to set up my differential equation dy dx equal to a function that is a function of x times a function of y. If I can't do that, then what I have is I have something that can't actually be separated. I can't use this technique, all right? So the thing about this is that not every differential equation can be solved using separation of variables. In fact, a lot of the other class of differential equations is how do I solve differential equations that can't be solved by separation of variables. So in this case, if I can do this, if I can transform my function into a function of x times a function of y, then I can actually use separation of variables. I get all my y's on one side, I get all my x's on the other, and then I integrate both sides. And that's it. That's really like the heart of the matter. That's the bread and butter of the whole thing, okay? Now, a couple of things that we have here, some tricks that we're going to see a lot inside of differential equations. One is to notice that if I take, if I want to get rid of the natural log, I have e to the natural log of some function, and I do that to both sides, what I'm going to oftentimes end up with is I'm going to end up with this transformation where I take e to some function with a constant in it, okay, and that becomes c times e to the function without the constant, right? And that's just from our power rules. And then finally, you can be kind of flexible when you go out and find your particular solutions. Pick a place where, you know, maybe the algebra is easiest to do if you're kind of doing this by hand. And in this case, that was right here. Okay? So this completes this video. I hope that doing separation of variables feels comfortable. It is pretty intuitive once you kind of get the heart of what it is that we're doing. All right. This concludes the video.